We're going to go ahead and take a look at related rates today. For the most part, related rates is looking at how things change over time. So we'll be doing lots of derivatives with respect to time. Now, you've been used to doing derivatives with respect to x, but now we'll be doing derivatives with respect to time because you think of velocity, it's like meters per second, where time is on bottom. So we're going to be doing a lot of that today. So for this first initial problem, we have a rocket that's 3 miles from a radar station that's being launched. The vertical speed of the rocket is what we're wondering about when it's 5 miles from the radar station, and that distance is increasing at a rate of 5,000 miles per hour. In other words, if this is where the rocket's being launched from, this is our radar station, this would always be 3. So if we look at this, we have our rocket being lifted off, bing, going straight up. You'll notice these two sides change. If two things change, well, it doesn't have to be two things, but if things change, we want to let variables represent those. We don't know these two. I'm choosing to use y and x. Now, whenever you're dealing with a rate, like here, we're looking at a rate because you're looking at speed. Here we're looking at the speed of the rocket from the radar station. No, we're looking at vertical speed here. So we're looking about the speed of this. So that would be the derivative of y with respect to t. That's what we're trying to find out. Now, here we have the distance from the radar station. Well, that would be this. And then it's increasing at a rate, so that distance is increasing at a rate. So that's our derivative of that. Any rate's going to be a derivative. So we have our distance from the radar station is 5, and we have our derivative of z with respect to t would be our rate, which would be our speed. So any derivative or rate is your derivative, which typically is going to be your speed, your rate of change. Now, for the most part, you want to find an equation that relates everything we have in our diagram. Well, it's a right triangle, so we know we could go ahead and do a squared plus b squared equals c squared. Now, we know at the instant that our 5 right here for z, we know that y would be 4. Well, how do we know that? Well, Pythagorean theorem, 3 squared plus y squared is equal to 5 squared. So you subtract 3 squared from both sides, you get plus or minus 4, but in the context of the problem, we can't have a negative value for our height. So that's what we have. Now, you don't want to be plugging in y being 4 and z being 5 here and taking your derivative, because everything would be numbers being constants. You take the derivative, you get 0 over 0. It would not help you. These two things change, so you're not going to plug in those values for anything until after you've taken your derivative. So we'll do our derivative. Derivative of 3 squared, or derivative of 9, you know, is 0. Then we'll go ahead and we'll do our derivative of y squared. So you put the 2 in front, decrease it by 1. Then we have to take the derivative of y with respect to time. So it's a dy over dt. Right-hand side, we'll do, so it's really just the chain rule. We were doing dx's over dx's and dy's over dx's before. Now, instead of going with respect to x like we did in previous sections, we're going with respect to t because we're dealing with time that we're comparing it to. So exponent in front on the right-hand side, decrease it by 1. Derivative of the z with respect to time. So now you'll notice you could just divide both sides by 2. Now we could throw stuff in here. We know y is 4. We're wondering what dy dt is. We don't know that. But z, on the other hand, is our 5 up here. We'll throw that in there. Our dz dt is 5,000, so we'll throw that in here. Huh. Well, we should be able to get that on one side by itself. So we get dy over dt equals, we'll get 25,000 divided by 4. So we get 6,250. But we're going to have units here. Your units have to be the units of y over the units of t. Y was measuring distance, which is in miles. Our time, or units of time in this case, is hours because it's miles per hour. So your units are always given to you by what you have here. The units of this over the units of this. So that's our first related rates problem. So for the most part in solving related rates, you're going to probably have to read it multiple times, draw a diagram, let variables represent the things that are changing. If you have some things that don't change, put a number there like you're supposed to. Then write down what it is you're given. Write down any rates you know. Remembering a rate is a derivative. Write an equation that relates all your variables, and then you just have to take your derivative of both sides with respect to time, and then just throw stuff into that derivative and solve it. So here we have a rectangle. It's because it was driving along and it got in an accident, so that's why it's a rectangle. So the length of our rectangle is decreasing at a rate of 5 centimeters per second, while the width is increasing at this rate. So in other words, if we look at this rectangle, so we have our rectangle, the length is decreasing, our width is increasing. So in other words, it's like this. Width getting bigger or shorter, length getting bigger. So that's one way to look at it and visualize it. At what rate is the area changing? When the rectangle is 100 long and 50 wide. So we know the two sides change, so I chose to use x and y. Could you use L and W? Yes, that would work nicely too. So we have the length right here is decreasing at 5 centimeters per second. That's a rate. So it's decreasing, so it's negative. Our width, the y, is increasing at a rate. So that's your dy over dt. Increasing, so it's positive. We also are looking at the instant when our rectangle is 100 long and our length here is dealing with x and 50 wide. And remember, our width is dealing with y. We're also going ahead and we're looking for the rate of change of the area. Rate of change is your derivative, so it's the derivative of area. So we're looking for a dA dt. We don't know what it is, so it's a question mark. So our variables are x, y, and a. Well, that's area of a rectangle, so we'll go a equals xy. So that's our equation that relates our variables. We have everything written down here that we were given or are looking for. All we have to do now is do our derivative of our area equation. Derivative of area with respect to time. So derivative of a with respect to time. Now notice the right side. It's a variable times a variable. Product rule! Cool! Derivative of the x with respect to time times the second plus the first, which is x, times the derivative of the second, which would be the derivative of y with respect to time. Well, at this point, we just have to go ahead and throw stuff in. So we throw in our dx dt, negative 5. We throw in our y, which is the 50. We throw in our x, which is the 100. We throw in our dy dt, which is our 3. So we get 150 plus negative plus 300. So we get 100. No, not 150. That's 250 negative plus 300. So we get 50 centimeters squared per second. You might be wondering, oh, where does this come from? Well, remember, it's got to be units of area So our length was in centimeters. Remember, area is units squared, so it's got to be centimeters squared with respect to the time. And the only time we had up here were always with respect to seconds. So it's area units over your time units. So this one we'll look at. So pause and read through. So it's a two-part problem. We have this sphere increasing at a certain rate, a constant rate, and for the first part, the radius of the sphere is 15. And we have our rate. Our radius is increasing at a certain rate, so it's a dr dt. So we're looking for the rate of change of the volume. Well, rate of change is a derivative, so it's derivative of volume, so it's a dv dt is what we're looking for. Well, what's relating our variables here of our radius to our volume of a sphere? Well, it's the formula for volume of a sphere. V is equal to 4/3 pi r cubed. So we need to go ahead and take our derivative of this with respect to time. So derivative of v with respect to time. Notice there's only one variable over here because pi is not a variable, pi is a number. So we just put the exponent in front, which cancels out the dividing by 3. So we get 4 pi, decrease your exponent by 1. Derivative of the inside, a dr dt. So now we can just go ahead and try to find our dv dt because we know r is 15. Plug it in. We know our dr dt is 5, or 0.5, sorry about that. And then we could throw that in our handy dandy calculator or do it in our head, and we get 450 times pi inches cubed per second. So we're dealing with units of volume over units of time. Our only length was in inches, but remember volume is your units cubed, so it's inches cubed per second. Now, for the second part of this question, it is when the volume and radius of the sphere are changing at the same rate. Oh, we're wondering what's the radius. So we're wondering what's the radius when the rate of change of the volume and rate of change of the radius are the same. Well, we already had done our derivative. Now, if we have two things that are identical, because you're told that this is equal to this, well, you could really divide both sides by them because they're both the same. Well, if they're both 7, you divide by 7. If they're both 8, you divide by 8. They basically disappear, so you get 1 on the left is equal to 4 pi r. Well, all we have to do now is finish solving this for r, so we can divide both sides by 2 or 4 pi. Take our square root of the top, square root of the bottom. Remember the square root of 4 is 2, square root of pi. Oh, we don't want to leave that root in the bottom, so you get the root out of the bottom, so you get the square root of pi over 2 pi. We're dealing with our radius, which is a length, so it's going to be in inches.